this video is on the second law of thermodynamics. To review, the first law of thermodynamics is that energy can be converted from one form to another, but energy cannot in itself be created or destroyed. The second law of thermodynamics is that the entropy of the universe increases in a spontaneous process, but remains unchanged in an equilibrium process. The connection between entropy and spontaneity of a reaction is expressed in this law. So in a spontaneous process, the sum of, so this is the total entropy of the universe, it's a sum of both the systems and the surroundings. It's going to be greater than zero. And in an equilibrium process, that change in entropy for the universe, the sum of the system and surroundings is going to equal zero. Now, it's possible in both of these scenarios for the change in entropy for the system or surroundings to be negative. As long as the sum of the two for spontaneous process is greater than zero, or equals for a spontaneous process, or equals zero in the case of an equilibrium process. So it's possible to have negative entropy in a spontaneous process for one of these two values. The sum needs to be greater than zero. Okay, so to calculate the change in entropy for the universe, we need to know the change in entropy for the system and the surrounding. Let's start by focusing on the system itself, or typically the reacting species. Now we're going to represent those reacting species using the letters A, B, C, and D, and their coefficients with the lowercase values of those same letters. Okay. The standard entropy of a reaction, so much like standard enthalpy of a reaction that you saw earlier in thermodynamics, is the entropy change for a reaction carried out at 1 atmosphere, so normal atmospheric pressure, and 25 degrees Celsius, roughly room temperature. Much like other state functions that you've seen thus far this year, the standard value is a measure of the sum of the coefficients times the values for the products minus the coefficients, the sum of the coefficients times the values for the reactants. All right, it's final minus initial conditions, just like other state functions you've seen in thermodynamics. So let's get some practice for calculating these. You can think in a very general aspect, or you can think more specific with standard entropy values. A general way of thinking of these is just looking at the number or the change in the number of gas particles. If the change in gas particles from left to right side is positive, as you'd see in calcium carbonate decomposing, the entropy will be positive. If it is negative, as you can see from 4 particles on the left side to just 2 on the right side for part B, it's going to be negative. And if there is no change in gas particles, you're going to have the smallest change in entropy. But let's get the exact numbers just to back up what we're doing. Let's look at this first one for calcium carbonate decomposing. You see a very large positive entropy, which makes sense. There's an increase in gaseous particles. For part B, you can see how they multiply the values times their coefficients, and you subtract the sum of each value multiplied by its molar coefficient. This has a net negative change in gaseous molecules, so you have a large negative value. And C has a much smaller value in terms of delta S because there is no change in the number of gaseous particles. But there is change in complexity of the reacting species, so you do have a change in entropy in this value as well. So entropy changes in the system. So a quick review of what we just did. When gases are produced, a reaction, if it produces more gas molecules than it consumes, that change in entropy is going to be greater than zero. If the total number of gas molecules diminishes, it decreases. That change in entropy is going to be less than zero. And if there's no net change, it may be positive, maybe negative, but it's going to be a much smaller number. All right, so this allows us to predict entropy changes of the system without actually knowing the values as well. You can see you went from 3 gaseous particles to none. So I'm expecting A to have a negative value for entropy. B, you see a solid going to 2 gaseous particles. You expect a positive change. And C, you see that there's going to be a slight change. You don't know if it's going to increase or decrease, but your prediction is that it's going to be very small. So delta S is positive in B. And you can't predict the sign of delta S for standard entropy for C, but it's going to be small in magnitude. You'd have to have the actual values to get an actual number. So all of that was to figure out the entropy change of a system. Now, remember, going way back, for a spontaneous or an equilibrium process, it's about the change in entropy of the system plus the change in entropy of surroundings. So we just focus on the system there. Now let's focus on the surroundings. So two scenarios. One is a exothermic process. One is an endothermic process. In an exothermic process, we'll focus on this left one first. You can see that heat is transferred from the system, so the reacting system, to the surroundings. Heat is released, which increases the molecular motion of the surroundings and thus increases the microstates of surrounding particles. So the entropy of the surroundings is going to increase in an exothermic process. It's going to do the opposite in an endothermic process. You're removing the system by absorbing energy from the surroundings, is taking away that, molecular motion from the surroundings and decreasing the entropy. One thing in terms of our calculations that we have to factor in is the temperature of the surroundings that it starts with. If the temperature is, say, high in the surroundings, molecules are already very energetic. So therefore, the absorption of heat from an exothermic process, for example, this one on the left, will have relatively lower impact if the temperature is high. If the temperature is very low, it's going to have much higher of an impact. So I see the formatting's a little tough here, but delta S of surroundings is equal to negative enthalpy of the system divided by temperature. There's a negative sign in front of the enthalpy of the system because if it's exothermic, you're going to get a positive sign, negative times negative. You're going to get a positive sign for entropy of the surroundings. Now, it's going to be more positive if the temperature of the surroundings is lower. It's going to be less positive if the temperature of the surroundings, this is delta H of system divided by T. The formatting was a little messed up, but you're going to see less change if the temperature is already high of the surroundings. So this is a way to quantify the change in entropy of surroundings, a very important equation. So we've related entropy to microstates, and the greater number of microstates we have, greater entropy. The third law of thermodynamics helps define an absolute value at which entropy starts. Now, it says that the entropy of a perfect crystalline substance is zero at the absolute zero of temperature. This is very convenient because in a perfect crystalline solid, now no imperfections in the crystal, it's an absolute perfect crystal, and at absolute zero, if the microstates are factored in, you can only have one arrangement that those particles could be in to be in a perfect crystalline solid. So W will be 1, and if you take a natural log of 1 based off of the Boltzmann equation we saw in our first video, you're going to have a value of entropy that's 0, okay? Now, as the temperature increases from this 0 value, you can see that you have more molecular motion, and you increase as you increase temperature. Then you see a very stark uptick in entropy at a phase change, where you actually undergo a change in complexity of the substance that you're working with. You'll see an even greater uptick in the evaporation point, the boiling point. So entropy increases with temperature, and it also increases pretty drastically when you undergo a phase change, because in those phase changes, you're spreading the dispersal of energy of those particles to a less ordered state. You have more disorder. You're going to have a greater standard entropy. Now, what's really convenient about entropy and the fact that we have this third law is that it enables us to determine absolute values of entropy. It's not based off of an arbitrary number where we say it is at this starting point. The starting point is well defined as 0 because it's a perfect crystalline solid at absolute zero. So the change in entropy for these substances is an absolute change. All right. Now, other than that, you work with entropy in the same way you work with other state functions in this chapter.